In part one of this lecture, we stopped on existential instantiation. We now need to continue through existential generalization. The rule of inference that is used to conclude that there exists x, p of x is true when a particular element c in the domain with p of c of true is known. That is, if we know one element c in the domain for which p of c is true, then we know that there exists p of x is true. Example, we conclude that there exists a woman who is wise from the knowledge that Lisa, a woman, is wise. Example 12. Show that the premises, everyone in the discrete mathematics class has taken a course in computer science and Marla is a student in this class, imply the conclusion that Marla has taken a course in computer science. Premise. D of x is a student in a discrete mathematics class. C of x has taken a course in computer science. Argument. For all x, D of x implies C of x. Everyone in this discrete mathematics class has taken a course in computer science. D of Marla is a student in the class. C of Marla has taken a course in computer science. Step 1. Statement, for all x, D of x implies C of x. It's a premise. 2. D of Marla implies C of Marla. Universal instantiation from step 1. 3. D of Marla. Premise. 4. C of Marla. Modus ponens from steps 2 and 3. Example 13. Show that the premises, a student in this class has not read the book and everyone in this class passed the first exam, imply the conclusion, someone who passed the first exam has not read the book. Solution. Propositional function, C of x is in this class, B of x has read the book, P of x has passed the first exam. Premises. There exists x, C of x, and not B of x. There exists a student in the class who has not read the book. For all x, C of x implies P of x. Every student in this class has passed the first exam. There exists x, P of x, and not B of x. There exists a student that passed the exam and did not read the book. Step 1. There exists x, C of x, and not B of x. It's a premise. 2. C of A and not B of A. Existential instantiation from 1. C of A, simplification from 2. For all x, C of x implies P of x. It's a premise. C of A implies P of A, existential instantiation from 4. 6. P of A, modus ponens from 3 and 5. 7. Not B of A, simplification from 2. 8. P of A and not B of A, conjunction from 6 and 7. And 9. There exists x, P of x, and not B of x, existential generalization from 8. Combining rules of inference for propositions and quantifying statements. For all x, P of x implies Q of x. P of A, where A is a particular element of the domain, therefore Q of A. This is universal modus ponens. Example 14. Assume that for all positive integers n, if n is greater than 4, then n squared is less than 2 to the n is true. Use universal modus ponens to show that 100 squared is less than 2 to the 100 power. P of n is greater than 4. Q of n squared is less than 2 to the n. The domain of n is all positive integers. For all n, P of n implies Q of n. For all positive integers n, if n is greater than 4, then n squared is less than 2 to the n. P of 100, 100 is greater than 4. Q of 100, 100 squared is less than 2 to the 100. Universal modus ponens. Now we go on to do some exercises that are similar to the ones that are assigned for this section. Find the argument form for the following argument and determine whether it is valid. Can we conclude that the conclusion is true from the premises if the premises are true? If Socrates is human, then Socrates is mortal. Socrates is human, therefore Socrates is mortal. Propositional variables. P, Socrates is human. Q, Socrates is mortal. P implies Q, P, therefore Q. Premises are commutative. The argument is modus ponens, and the conclusion is true if the premises are true. 5. Use rules of inference to show that the hypothesis, Randy works hard. If Randy works hard, he is a dull boy. If Randy's a dull boy, then he will not get the job. Imply the conclusion, Randy will not get the job. Propositional variable. W, Randy works hard. D, Randy's a dull boy. J, Randy will get the job. Hypothesis. W, Randy works hard. W implies D. If Randy works hard, then he is a dull boy. W implies not J. If Randy is a dull boy, then he will not get the job. Desired conclusion, not J. Randy will not get the job. Step 1, W, that's a hypothesis. 2, W implies D, that's another hypothesis. 3D, modus ponens using 1 and 2. 4, W implies not J, it's a hypothesis. 5, not J, modus ponens using 4 and 5. 17, what is wrong with the argument, let X be X is happy, H of X be X is happy? Given the premise, there exists H of X, we conclude that H of Lola, therefore Lola is happy. We know that some X exists that makes X of X true, but we cannot conclude that Lola is one such X. Maybe only Suzanne is happy and everyone else is not happy. Then there exists X is true, but H of Lola is false. 23. Identify the error or errors in this argument that supposedly show that if there exists X, P of X, or there exists X, Q of X is true, then there exists X, P of X, or Q of X is true. Step 1. There exists X, P of X, or, there exists X, P of X, and there exists Q of X. That's a premise. There exists X, P of X, simplification from 1, P of C, existential instantiation from 2, 4, there exists X, Q of X, simplification from 1, 5, Q of C, existential instantiation from 4. We cannot assume that the C that makes P true is the same C that makes Q true. This is the error. And 6, P of C and Q of C, conjunction from 3 and 5. And finally, there exists X, P of X, and there exists X, Q of X. Existential generalization. And that concludes our discussion of rules of inference.